All right, so this is part two of the transformations of absolute value functions. All right. So yesterday we rewrote g of x in terms of f of x. We're going to do that again today. We're going to describe the transformations. We had horizontal, vertical shifts. We had reflections over the x-axis. And today we're going to work on vertical, stretch, and shrinks. And again, we're going to identify the vertex and then graph. All right. So if we go back to, if we look at this screen here, so we have f of x equals, but before actually I get there, let me add one screen. All right, so let's go back to this original function. So f of x equals a times the absolute value of x minus h plus k. And let's talk about a again. So we did two things. We did one thing with a yesterday. We said if a is equal to -1, then what does this tell me about what kind of transformation is this? Yeah, so this is going to be a reflection over the x-axis. So reflection over the x-axis. And now let's put some numerical numbers there besides -1. Let's say, what if a is greater than 1? So if a is greater than 1, let's say we have a 2 there, or a 5, or whatever, then this is a vertical stretch by a factor of a. So hypothetically, if I had f of x equals 3 times the absolute value of x, this would be a vertical stretch by a factor of 3. And then if a is between 0 and 1, so if a is greater than 0 but less than 1, so any fraction, then this is a vertical shrink by a factor of a. And again, the example here would be, let's say f of x equals 1/2 times the absolute value of x. I would say this is a vertical shrink by a factor of a. So if you think about these graphs, shrink and stretch, stretch gets bigger, shrink gets smaller. So vertical stretch, you want a number that's a little bit bigger. So when you say by a factor of a, it's going to be a number that's a whole number, right? By a factor of a. When you say vertical shrink, it's getting smaller, right? You think of a shrink, something small. It's not a whole number, but more of a fraction. So shrinks go with your fractions, stretches go with your whole numbers. So let's take a question here. So the question is, what if it's less than -1? So let's say we're looking at an example here. Let's say we have g of x is equal to -2 times the absolute value of x. Okay. So this -2 doesn't fall between a is greater than 1 and a is less than or equal to, or greater than 0 and less than 1. So how I'm going to look at this is actually separate. I'm going to take a look at this as a negative sign. That's my a is equal to -1. And I'm going to look at the 2 separately. And this is my a is greater than 1. So the -1 is a reflection over the x-axis. And the 2 is a vertical stretch. So it's still going to be a stretch, just reflected over the x-axis. So we're going to actually graph 3 different functions on this one graph. We're going to look at our parent function, f of x equals the absolute value of x. Right, so this is our parent function that starts at the origin, and it goes up 1, right 1, up 1, right 1, and so on. And I'm just going to graph, so let's put our original function on there, or our parent function on the graph. And we got our parent function. Now let's see what the g of x equals 3 times the absolute value of x does. So we said from the previous slide that this 3 is going to be a vertical stretch by a factor of 3. If we rewrite g of x in terms of f of x, we could say that this is going to be g of x equals 3 times f of x, with the 3 on the outside. My vertex here, the vertical stretch or shrink does not affect the vertex. Okay, my vertex here, the h is 0, the k is 0, so my vertex is still 0, 0. And now let's graph this. Okay, so I'm going to make myself a little table here just so I can get some values, and I'll show you what the x does. Okay, so we got x and g of x. I'm going to use my vertex 0, 0. I'm going to put that right in the middle, so that point doesn't change. If I go 1 unit to the left, 1 unit to the right of the vertex, if I plug in -1 into my function, what's the absolute value of -1? Times 3. So absolute value of -1 is 1, times 3 is 3. And the same thing will happen if x is 1. Absolute value of 1 is 1, times 3 is 3. And if I plug in -2 or 2, absolute value of -2 is 2. 2 times 3 is 6. And we got that. So now we have 5 coordinates there. So if I go -1, rise 3, I'm going to go left 1, up 3. Or right 1 and up 3. Or left 2, up 6. Or right 2, up 6. And this is the absolute value with a vertical stretch of 3. So a vertical stretch actually makes the graph a little bit more narrow. Okay? So the graph is a little more narrow when we have a vertical stretch.
So this is like basically the same thing as like dilations when you multiply everything by a number.
Very similar to dilations, yeah, absolutely. All right. Let's take a look at one more on the same graph. All right. But rather than saying g of x equals 3 times the absolute value of x, let's go p of x equals, let's go 1/3 times the absolute value of x. So we can see the difference of what a 3 does to your function and what a 1/3 does to your function, right? A vertical stretch of 3 versus a vertical shrink of 1/3. All right. So again, this is going to be the 1/3 here is going to be a vertical shrink this time by a factor of 1/3. Rewriting this would be p of x equals 1/3 times f of x. My vertex is still 0, 0. And now I'm going to make myself another little table here. Let me steal this table. And I'll make myself a little table here in purple for my new function p of x. So I got x, p of x. And my vertex, again, I'm going to go 0, 0. This one I'm going to be a little more picky about the numbers I choose. Right? So I don't want to choose -1 on this one like the last one, because I know I'm going to multiply by 1/3 afterwards. So what's a nice number to choose? Yeah, I'm going to choose -3 or +3. And another one, I'm going to choose one more. The next nicest number to choose would be, -6 and +6, right? So when I multiply by 1/3, I'll get whole numbers. So if I plug in -3, the absolute value of -3 is 3, times 1/3, I get 1. Absolute value of -6 is 6, times 1/3 is 2, and these are going to be symmetric and be exactly the same. And now let's graph p of x and see what a vertical shrink looks like in comparison to the absolute value of x. So 0, 0, still on my origin. -3, 1. 1, 2, 3, 1. -6, 2. 4, 5, 6, 2. And I'm going to go the other way. 1, 2, 3, 1. 4, 5, 6, 2. And I'm going to graph this one here in purple. So the vertical shrink makes my graph a little wider. Together what we did yesterday with the horizontal, vertical, And then let's throw this vertical stretch in here as well. Let's put this all together. All right, so first, we're going to rewrite g of x in terms of f of x. Who can help me do that? G of x in terms of f of x. Want it?
G of x equals 3 times f of x minus 2 out of parentheses minus 2.
Beautiful. G of x equals 3 times f of x minus 2 minus 4 on the outside. Excellent. What are my transformations? Give me 1. Give me a transformation. Give me 1 transformation. Yep.
Right to a horizontal shift 2 units right.
Beautiful. Horizontal shift 2 units to the right. Like it. Give me another one. Yep.
A vertical shift 4 down.
Vertical shift 4 units down. And one more. What is my last one? Beautiful. Vertical stretch by factor of 3. Awesome. What is my vertex? Bless you. What is my vertex? What is the vertex here? Yep, my vertex is 2, negative 4. Okay. This is my h. This is my k. All right, so the vertical stretch does not affect the vertex. All right, last but not least, let's graph this bad boy. And we're going to do a little graph here just to make sure. And now we could do it with the slope as well. So we got f and g of x, but we'll verify. I'm going to start with my vertex, which is 2, negative 4. The x value of the vertex is 2. I'm going to pick 1. I'm going to pick 2 units to the left. I'm going to pick 1 and 0. I'm going to pick 2 units to the right of that. I'm going to pick 3 and 4. And now I want to show you how the slope is applied as well. So the slope here is going to be the product of the coefficient in front of the absolute value and the coefficient in front of the x. Right? The slope is a product of the coefficient in front of the absolute value and the coefficient in front of the x. Okay, so the coefficient in front of the x is 1. Coefficient in front of the absolute value is 3. 3 times 1 is 3. So we have a slope of 3. And again, I'm going to use my table just to make sure I'm on the right track. So 2, negative 4 is my vertex. 1, 2, 1, 2, 3, 4. I'm here. Okay. So if I use my slope, I have a slope of 3, so I should rise 3, 1, 2, 3, and run 1. Let me verify that, right? If I plug in 3 into my function, what's 3 minus 2? 1. The absolute value 1. 1 times 3. 3 minus 4. Did I get negative 1 here as a y value? Yep. So once I have this one, remember, this is going to be symmetric. So if I go 1 to the right, I'm here. 1 to the left, I should be here. So I could kind of shortcut that one a little bit. And then again, I'm going to use my slope again from this point. 1, 2, 3, right 1. And I can do the same thing. 1, 2, 3. Left one. And then here we go. And then let's just make this last line. And connect my dots. Okay, and now we have our transformations. We have our vertex. We wrote g of x in terms of f of x. And we graphed our function.